We'll be looking at historical free-wheeling and Hansch approaches. You'll be wondering what historical free-wheeling and Hansch approach is all about. There are two methods or methodology used in QSA. I know by now you should be familiar with this word, QSA. QSA means quantitative, structure, activity, relationship. And we know that in QSA, you're looking at the physiochemical properties of a drug that affect its biological activity and then representing it in an equation. So when you look at Hansch analysis, in Hansch analysis, a classical QSA method that combines multiple physicochemical approaches like the lipophilicity, electronic and steric effects of a compound to predict its biological activity. We know that in QSA, we consider a lot of physiochemical approaches, and then we talked about three major ones or three ones that are used to summarize or represent all the physiochemical approaches. So in QSA method, you're trying to look at physiochemical approaches like the lipophilicity, and we know that when we talk of lipophilicity, we are looking at the partition coefficient and the pi substituent constant, but in this case, the partition coefficient. You're trying to find out how the partition coefficient of a drug affects its biological activity. You're also trying to find out how the electronic effects, we've discussed electronic effects, and we know that electronic effect has to do with the effects of the substituent, the electronic effect of substituent like electron withdrawing group and electron donating group on the molecule. Also, you're also considering the steric effect, that's the size or shape related effects of the molecule or the compound. You're trying to consider how the size or the shape of the molecule or the substituent affects the biological activity. So you're trying to consider these three major physiochemical properties in QSA. You're trying to use them to predict the biological activity of a drug. And we know that you can modify a lead compound. I'm using this as an instance. Let's say this is a drug molecule. This is a lead compound. We're still using this again. If this is a lead compound, you can modify these compounds by maybe checking out how the lipophilicity is affecting the biological effect. If you find out that, okay, this very drug compound will give us more effect or will be able to cross the membrane more if we change or increase its lipophilicity, that means you can alter some substituents, alter some bonds, alter some part of this molecule in order for you to get a drug that will be more lipophilic. And that also happens to electronic effects and also steric effects. So in Hansch analysis or approach, you have a formula, and it's log 1 over C equals to A log P plus, the log P here is partition coefficient, and this is the electronic parameter, plus CES. ES is the steric effect, and this D is a constant. And you'll be wondering what A, B, and C is. The A, B, and C are regression coefficients. They are regression coefficients. So you'll be wondering, what is regression? Regression is a statistical method, or is an inferential statistics, where you're trying to know the direction or the strength of a relationship between two or more factors. Let's say that it's been established that the lipophilicity of a drug has a relationship with its biological activity, and that is what correlation does. Correlation helps you to establish or find out if there's actually a relationship between the two factors or two or more factors that you're considering. Whereas what regression does is that if correlation says that there is a relationship, so what regression will tell you now is, what is the direction of this relationship? What is the strength of this relationship? And then when I introduced this topic, I said that when your regression coefficient is greater than 0, it means that there is a positive relationship. When your regression coefficient is less than 0, it means that there is a negative relationship. And when you talk of positive relationship, it means that I'm using let me use lipophilicity as an example. It means that if you increase the lipophilicity of that particular compound, you are also increasing the biological activity. Or when they say it's negative, it means that there's an inverse relationship. That means if you increase the lipophilicity, if you increase the number of lipophilic substituents of that molecule, that means you are reducing the biological activity. Another thing too is when your regression coefficient is when it's close to 1, you will say that the relationship is very strong. And when it is close to 0, you say that the relationship is very weak. So we've been able to establish that regression coefficient is a statistical method that helps us to describe or helps us to predict the strength of the relationship between the physiochemical properties of a compound and its biological activity. It helps us to predict the strength. It also helps us to predict the direction of this relationship. And that's if your coefficient is greater than 0, it means that there's a positive relationship between the two factors you're considering, and in this case, the physiochemical properties and biological activity. And then when it is less than 0, there's a negative relationship. When your coefficient is close to 1, it means the relationship is very strong. And then when it's close to 0, it means that there's a weak relationship. And let me give an example. If you say that your relationship is very strong, it means that lipophilicity, if you're saying, if you get a coefficient that is greater than 0, and let's say it's close to 1, it means that, let me give an example with lipophilicity. It means that the more lipophilic that drug is, the more the biological activity, and also the effect, or it's not something that you can maybe overlook. It means that it has a very strong relationship. So it's actually a key determinant factor in the biological activity or the potency of a particular drug. So as we've established that, let's go back to our formula again. So we already know that A, B, and C is regression coefficients, and then the D here is a constant which can also generate statistically. So the log 1 over C, the C here means the concentration of the drug needed for biological activity. So in this Hansch approach, you're trying to consider the effect or the contribution of log P to the concentration of this drug or this compound that will be needed to elicit a therapeutic activity. You're also trying to consider the contribution of the electronic effect and also the contribution of the steric effects on the concentration. So when you generate all these things, it can also give you an idea on how much or what concentration of this particular compound or this molecule will be able to elicit effect, and not just the concentration. If you can optimize these parameters like log P, this, and this, that means you'll be able to design a drug that will elicit its effects, that will elicit its therapeutic effects with minimal side effects, with minimal adverse effect, or maybe minimal negative effects. So I gave an example. Let's say that you ran a Hansch analysis, for instance, and then you came up with this result. Let's say you got your A, which is the strength or direction of the relationship between log P, which is partition coefficient, and your biological activity. Let's say you got 0.5. So from the illustration I gave on regression coefficient, that this should show you that there is a positive relationship between lipophilicity or partition coefficient and the concentration of a drug needed for biological activity. Or you can say that there is a positive relationship between lipophilicity and the biological activity of a molecule or the molecule you are considering. So if you get 0.2, looking at 0.2 here, we have this 0.8 shows the contribution of the electronic effect. So that means that there is actually a positive relationship between electronic effects and biological activity. So that will tell you, when we discussed on electronic effects, we said that electron withdrawing group, that they increases the electronic effects of a molecule or electronic effect of a substituent on a molecule. So it means that if we are having 0.2 here as the regression coefficient and also 0.8, it means that the more the electron withdrawing group, the more the biological activity of that particular lead compound or molecule. And also in this place, we're having a negative value here, which is minus 0.1. So that means that there's an inverse relationship between the steric effect and the biological activity. And that will tell you that the higher the steric effect, the lower the biological activity. And you know, when we are talking of steric effect, we are looking at the shape and the size of the molecule. So that means, let's say for instance, if your substituent is actually a bulky molecule or a bulky a bulky substituent. I gave an instance with 30 butyl. So that means the biological activity, of the lead compound you are considering will be reduced. So with this formula, you can optimize your drug design. With this can give you an idea or an overview of the key physiochemical parameters or properties that you have to consider while designing your drugs. So that's for Hansch analysis. So we're looking at the free Wilson approach. In the free Wilson approach, is also a QSAM method that directly relates the structural features / substituents of a compound with its biological activity. It's supposed to be an activity here. So let's say, for instance, this is a drug molecule. Let's say this is a drug molecule. Okay, let me use this. Let's say this is a drug molecule. I don't know if this exists, but I'm using this as an instance. In free Wilson, you're not considering the physical and chemical properties this time around in the way Hansch does. This time you're considering the structure of a drug. You're trying to consider the effect of the structure of a drug on the biological activity. So you're asking yourself, what is the effect of this unsaturation? That's this double bond here. What effects does it have on the biological activity of this drug? You're asking yourself, what effect does this substituent, this COOH we have here, what effect does it have on the biological activity of this drug? What effect? So you're looking at the structure, the molecular structure of that drug. You're trying to consider the effect these structures or the features or the substituents of that molecule. What effect does it have on the biological activity? So the key difference between the Hansch analysis or the Hansch approach and then the free Wilson. In Hansch approach, you're trying to relate the physicochemical properties of a drug or a molecule you're using it to predict its biological activity, whereas in free Wilson, you're considering the structural features or the substituent in order for you to predict the biological activity of that particular compound or molecule. Thank you.